All right, let's get into a classic showdown in the world of computer science. In one corner, you have the fast, optimistic strategist, Dijkstra's algorithm. And in the other, the cautious, super thorough Bellman-Ford. Today, we're putting these two legendary pathfinding algorithms head to head to see which one really comes out on top in the world of networks.
You ever wonder how your phone, in like a split second, finds the absolute fastest way to get you somewhere, weaving through traffic you don't even know is there? Well, the magic behind that is something called a shortest path algorithm. But as we're about to find out, not all paths, and definitely not all algorithms, are built the same.
So here's our game plan. First, we'll break down the core problem they're both trying to solve. Then, we'll meet our two contenders, explore the one critical weakness that really sets them apart, and then watch them duke it out in a real-world showdown. And finally, we'll talk about how you choose the right one for the job.
At its heart, the shortest path problem is all about finding the most efficient route through a network, or what computer scientists call a graph. Now, this could be a literal map of cities, but it could also be the ridiculously complex wiring of the internet, or even mapping connections in a social network. The goal is always the same: find the path with the lowest cost.
Okay, let's meet our first contender. Dijkstra's algorithm, which has been around since 1959, is pretty much the rock star of shortest path problems. It is incredibly fast, super efficient, and that's why it's the default choice for so many different applications.
The secret to Dijkstra's speed is its greedy approach. Now, what does that mean? It means it doesn't really plan far ahead. Imagine you're a hiker, and at every fork in the trail, you just take the path that looks like the shortest one, right in that moment. It's optimistic. It always assumes the choice it's making right now is the best one it'll ever find. And this is basically how it works. It starts where you are, and it pretends every other place is infinitely far away. Then it just methodically works its way out. It looks for the closest spot it hasn't been to yet, goes there, and then tells all the neighbors of that spot, hey, I might have found a faster way to get to you. It just keeps repeating that, expanding outward like a ripple in a pond. It's actually pretty elegant.
But, every hero has a weakness, right? And Dijkstra's beautiful, optimistic strategy has an Achilles heel. It has one major blind spot, and it's this really weird concept called negative weights.
See, the entire foundation of Dijkstra's logic, the reason it's so fast, is built on one simple, common-sense idea. Every step you take adds to your journey. You can't take a step and somehow get closer to where you started. Because of this, once Dijkstra finds a path to a place and marks it as the best one, it locks it in. It never looks back. That's its key to speed, but it's also its biggest vulnerability.
So what on earth is a negative weight? I mean, on a roadmap, it's totally impossible. But in other kinds of networks, it could represent something like earning money instead of spending it, or maybe gaining energy instead of using it up. It's a cost that's actually a benefit. And this is where Dijkstra's optimistic, never-look-back strategy just completely falls apart.
And that leads to the ultimate nightmare scenario: a negative cycle. Just imagine finding a loop. You can go around and around forever, and every single time you complete the loop, your total cost actually goes down. You can just keep looping forever, getting a better and better score, all the way to negative infinity. The whole idea of a shortest path just stops making sense, and Dijkstra gets totally lost.
And that brings us to our second contender, the Bellman-Ford algorithm. It's not as flashy, it's definitely not as fast as Dijkstra, but it was specifically designed to be more careful, more methodical, and to handle these weird situations that Dijkstra just can't. So if Dijkstra is a greedy sprinter, you can think of Bellman-Ford as more of a cautious marathon runner. It doesn't assume anything, it's skeptical. It methodically checks and rechecks every single path in the entire network over and over again until it's absolutely positive it's found the best possible routes. The process itself is straightforward, but it is exhaustive. It just loops through every single connection in the network. On each pass, it asks for every path. Hey, did I just find a shorter way to get here through one of my neighbors? It does this a whole bunch of times. Then, and this is the clever part, it does it one last time. If it still manages to find a shorter path on that final run, it knows it's caught in one of those nasty negative cycles, and it sounds the alarm. So we have the fast, optimistic algorithm and the slow, cautious one. But how do they actually stack up in the real world? Well, a 2015 performance analysis put them to the test in some really practical network routing scenarios. The study basically set up two different battlegrounds. First, a nice, stable, predictable wired network,
the kind of thing that forms the backbone of the internet, where stuff doesn't change very often. And second, a chaotic mobile network where devices are constantly moving around, connecting and disconnecting. Total chaos. And the results are pretty fascinating. If you look at the top half of the table for that stable network, Dijkstra was the undisputed champ. I mean, over 3 times faster and used less memory. No contest. But then, look at the bottom half for the dynamic network. The tables turned completely. Bellman-Ford was over 5 times faster at adapting to changes, and it created way less network chatter. Let's just focus on that number for a second. In a big network with 1,000 nodes, Dijkstra figured out all the best paths in just 58 milliseconds. That is blazing fast. It's absolutely perfect for a stable network where you can be optimistic. Calculate the routes one time, and you're pretty much good to go. But now look at this. When the network was constantly changing and breaking, Bellman-Ford managed to stabilize all the routes in less than a second. Dijkstra's optimistic approach of just recalculating everything from scratch every time something changed, that took a painful 4.6 seconds in a networking that is an eternity. Bellman-Ford's skeptical, step-by-step updates were just way more efficient. So, what does all this data really tell us? Well, it proves a classic engineering principle. There is no single best solution for everything. It's all about picking the right tool for the specific job you're trying to do. So the conclusion is actually really clear. For stable networks, like a company's internal system running a protocol like OSPF, where speed is everything and path costs are predictable and positive, Dijkstra is your champion. But for messy, dynamic environments like mobile ad hoc networks, where things are constantly moving and connections are unreliable, the cautious and adaptable Bellman-Ford is the much smarter choice. And as the researchers themselves put it, this wasn't a fluke. The results were solid, no matter how they set up the networks. Each algorithm has a place where it just shines. The raw speed of Dijkstra in stable worlds and the resilience of Bellman-Ford in chaotic ones, that's the fundamental trade-off. And this really leaves us with a final, bigger thought. The choice between these two isn't just a technical one. It's almost a philosophical one. In a world where our data and our networks are getting more complex and more dynamic every single day, what do we value more? The raw speed that comes from an optimistic guess, or the cautious safety that comes from a guaranteed to be correct answer? The answer, as always, really depends on what you're trying to build.